Okay. Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Afifa dan Pembangunan my state number is 212035177. So I want to present about project briefing. So as you can see, the slide is project information and location. So the project title is Cadangan Pembangunan Perumahan Fasa 9 unit yang mengandungi satu, dua unit rumah teres, dua setengah tingkat. Dan satu lagi, 7 unit rumah teres, dua tingkat. Beralamat PT 474 SXD 197916 Meeting Center dan PT 6175 HSM 18978 Section 53 Banda Adasa Daerah Kota Cadangan. So we go to project area. Project area is 8 UT line 2668 meter. So the client the project is Larang Pasir. The one is Sini Prestasi Sembilan. The location is number 51 Perumahan, kawasan Pembangunan dan Jalan Baris Pusat. Akan 5050 Cadangan. So, objek arsitek is UUC. Maknanya dia bantuan orang berjaya dan durasi hasil dasar latihan. So, you can see the specific periodnya is located is PT So, during the second district
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azmi bin Muhammad Azmi. My metric number is 221203409. So today I will present about the drawing. So basically my part is I am responsible for the architectural and structural drawing for this IBS mini project. The selected building type is a terrace house, and for this project we focus on the middle unit, which represent the most repetitive and typical unit in a terrace housing development. So why we choose the middle terrace house? Because the middle terrace house was chosen is it shares party wall on both sides, so resulting in a more efficient in structural system. Since the layout is repetitive, IBS components such as precast wall, slab, and beams can be standardized and mass produced, which reduce the cost and the construction time. Okay, next, the key location plan. So basically, the slide show the key location of the terrace housing development. It indicates the orientation of the houses, access road, and the surrounding units. From an IBS perspective, this plan is important for planning the component delivery, stacking area, and the crane positioning, especially in a limited terrace housing site. Next is the front elevation plan and the ground floor plan for the middle unit terrace house. So basically, this house is a double-story house where it has the ground floor and the first floor. So in this plan, for the ground floor plan, the layout includes typical spaces such as living area, dining area, kitchen, and the bathroom. Next slide is the attic roof floor plan and the first floor plan. In this slide, it shows that the roof floor plan illustrates the roof layout and the supporting structural element. And for the first floor plan, the it consists of bedroom and bathroom arranged in a repetitive and symmetrical layout. The structural elements such as column and load-bearing walls are aligned directly above the ground floor, which is ideal for precast structural system and ensure the efficient load transfer. Next slide is the elevation plan for the rear view. In this slide, it shows only the view of the middle terrace house. It is because as a middle unit, the side elevation are shared with the adjacent houses, which reduce the external wall construction. So this allows IBS wall panels to be designed with uniform opening and finishes and improving consistency across the terrace room. Next is the modular plan. So in this slide, which is show the modular plan which is critical drawing in the IBS design. The house layout is divided based on standard modular grid that ensuring the wall slab and openings align with the IBS component size. This approach minimize material wastage and improve the manufacturing accuracy and increase the construction efficiency.
My name is Universiti, number metric 22120120. The project is divided into 6 plots, not including plots within label D to G in drawings. In this project, we only consider plot 33 for industrialized building system application. This plot has a total construction area of 226.52 meters square, including roof and area listed in table. The area after modular coordination is bigger than the actual area of the project. The industrialized building system is a construction approach that emphasizes the uses of prefabricated components manufactured in a controlled environment and subsequently assembled on site. The adoption of IBS aims to improve construction quality, enhance productivity, reduce dependency on manual labor, and minimize material wastage. This report presents the application of the IBS system for the Phase 5 housing development consisting of 9 terrace houses, namely 2 units of 2 half-story terrace houses and 7 units of 2-story terrace houses located in All-Star, Kedah Darul Aman. The application focused on modular coordination, structural loading selection, precast member selection based on JKR IBS catalog and technical integration. The conversion of conventional building dimension into modular grid line is a fundamental requirement in the application of modular coordination and industrial building system. Modular coordination is a dimension coordination system in which buildings and their components are dimensioned and positioned using a basic module and its multiple, allowing standard module components to fit together efficiently without excessive site modification. In accordance with the principles of modular coordination and Malaysian standard MS1064, the basic modulus adopted for this project is 1 modulus equal to 100 mm. In this project, we not only using horizontal modular coordination, which 3 module equal to 300 mm, and vertical modular coordination, which 1 module equal to 100 mm. We also standardize the building components, which are beam, columns, walls, and slab. The process transitioned from conventional cast in situ method to the use of standardized building components to align with the principles of the industrialized building system. The process is guided by the JKR IBS Catalog 2020, which provides a library of pre-engineering components designed for mass production and rapid assembly. The primary objective of standardization is to reduce design complexity and on-site labor while ensuring structural reliability. All the components is using the increment following the standard of Malaysia and as shown in the slide.
My name is Siti Laika and I will proceed for the beam, and then the beam is act as the horizontal member that transfer to the load from the slab to the column. In this project, beam width was standardized from the 125 mm until 230 mm to a 300 mm, and the depth also standardized to the 500 mm. And then I will show the table of this is actual size of beam, and then we upsize following the JKR standard because rectangular beam to the 300s times 500s. Okay. Okay, this also the table continue before this, and then we have the actual beam, and then we upsize following the JKR standard, and then we also list the code of selected cast beam that we choose for our beam size. Okay, I will proceed to the column, and then the column is provide the vertical support to the structure, and then the column size was standardized to the 300 times 300, and a 300 times 600 to match the beam size and a modular grid. So I attach the table of the standardized size for column from the actual to the upsize following the JKR standard. So next, I also list the code of a selected precast for the column.
After the increment, which is the upside of slabs, the flooring system utilizes precast half slab, which act as permanent formwork and provide the structural base for a thin layer of in-situ topping. To match the JKR IBS catalog, the slab thickness was upside and standardized to a total depth of 175 mm. This component is vital for achieving a high IBS score as it eliminates the needs of extensive timber formwork and scaffolding, providing an immediate, safe working platform for the first and above. The slide showing that the code of component we are using is HS85175, which the thickness is aligned with the upside's overall depth. For the wall system, the project utilizes prefabricated plain wall panels for all external walls. These panels were upsized from the original 150 mm brickwork thickness to a modular 150 mm thickness to align with JKR standardized component. The use of these standardized panels ensures superior thermal insulation, soundproofing, and weather resistance compared to traditional masonry, while the factory finished surfaces reduce the need for thick layers of on-site plastering. Due to the complicated geometry and not duplicated ground floor and first floor structural layout, the internal walls remain the conventional method. So as the floor height, the ground floor actually having the floor height of 3,350, but we upside to 3,500. While first floor having an actual floor height of 3,200, then we upside to 3,300. It's because to align with the JKR IBS catalog. In this project, the staircase system was intentionally designed as a conventional in-situ reinforced concrete element, rather than a prefabricated or precast IBS component. This decision was primarily influenced by practical and technical considerations related to site conditions, constructability, and cost efficiency. The staircase geometry requires close coordination with varying floor levels, landings, and architectural finishes, which would have necessitated customized precast modes. Such customization would reduce the economic viability of prefabrication, particularly for a project of limited repetition. Additionally, in-situ construction allows greater flexibility in accommodating dimensional tolerances, alignment adjustments, and on-site modification during construction, which is beneficial where tight spatial constraints are present. In this project, the structural loading will only consider dead load and lift load. All the calculations and assumptions are according to Eurocode 1 and Eurocode 2. However, the dead load of cell weight from precast structural components are taken from JKR IBS catalog based on the reinforced concrete density and manufacturer specifications. All the lift load were assumed in accordance with Eurocode 1 due to the location and the area in the architecture plan. For this part of list of drawings, we'll show the modular coordinated plans and the building information modeling products. These are the modular coordinated architecture floor plan. Well, these are the modular architecture section plan. And this is the modular structure plan that we already upsized the columns and beams and walls and slab in this project.
Next slide is the 3D structural drawing. This 3D structural model illustrates the load transfer system from the first floor to the ground floor. So it also helps in checking alignment, connection details and constructability of IBS component before construction begin. So basically this drawing using precast column and precast beam. So this is the 3D architecture drawing. In this 3D architecture model, it helps visualize the overall form of the terrace house, including the facade design. It clearly shows how IBS elements are integrated while maintaining the typical appearance of Malaysian terrace housing. So this model is created by using Revit software.
So I will proceed to the IBS core calculation, which is we have a three part. We have part one, structural system. Second part is a wall system, and the third part is others IBS component. So this is a formula that we use for the part one, part two, and also the part three for the others IBS component. So we go through the part one, which is the structural system. So this is a structural system which is we refer to table. First table is the for the column, beam, and slab. Second table for the roof, and a third table for the additional IBS factor. So we proceed to the next slide. So this is calculation for the structural system, which is we calculate for the ground floor. We also calculate for the first floor and the also roof. And then for the ground floor, we use the prefabricated beam and also column and also slab. So the IPS factor is 1.0. And then the porch for the ground floor, we use also prefabricated column and prefabricated beam. And but the slab is the in situ and the IPS factor is 0.7. And then for first floor, we also same types of beam and column, but no slab. So the IBS factor is also 1.0. And then the balcony also same to the porch. The IBS factor 0.7. And we have the additional factor, which is for the table 3. We have a 50%, which is the IBS factor is 0.02. And then the total construction area for our house is 4007.16, and then the IBS factor for the part 1, which is a structural system, is a 48.94 per 50. So proceed for the wall system.
Assalamualaikum and good night. My name is Naruddin and today I would like to present about calculation of IBS score on wall system. So I am calculating from the ground floor to the first floor, and I have two categories, which is external wall and internal wall. So for the external wall, I have used the prefabricated walls, and for the internal wall, I use the in situ concrete with permanent formwork, which is for the prefabricated panel. The IBS factor is 1.0, and for the in situ concrete with permanent formwork is 0.3. So as we can see for the ground floor, I calculated I did the ground floor perimeter with the first floor, and I get the IBS score, which is 12.68. And then for the external wall, for the internal wall, from the ground floor to the first floor, I get the IBS score calculation, which is 4.39, and I add for the two category, which is the external wall and the internal wall, I get the 70.70.
This category includes non-structural IBS components and standardized system. The first one is utilization of standardized components. In the IBS score calculations for this part, the first component is beam. There are 8 dimensions of beam in this project, and out of 49, 35 of them is using a standardized dimensions, which is 300 times 500 millimeters. Thus, for beam, the standardized of beam is set to 71% and obtain a point of 2. For column, there are 3 dimensions. All of the dimension is standardized. Thus, 100% of the column is using standardized components. Thus, the point obtained is 4. For slab, only ground floor and first floor using standardized components. Thus, 366.76 out of 381.16 is considered in this project is standardized. Thus, 95% of usage. So the point obtained for slab is 4. In this project, only external wall using standardized component. Thus, out of 173.1, 110.1 is standardized. So a 63% usage indicate that the wall obtained a point of 2. For door, out of 11 unit of door, only 6 is standardized. So a 55% of usage led the door component to obtain a point of 2. For window, none of the unit, only 3 of the unit using standardized dimensions. So it's only 43%, which means that the point obtained is 0. After the summary, the total point awarded for this part is 14 points. The second part in other IBS components is productivity enhancing solution and technology adoption. In this project, we are using building information modeling and is apply a beam level 2 between project team. Thus, the point obtained is 6. And for digitalization and virtualization, we're using augmented reality and virtualization, which we build out the 3D models and apply the VR technologies to obtain an IBS score of 1. And other enhancing solution is the usage of modular grid line in drawing. We use 100% of the modular grid line in this project. Thus, we obtain a point of 6. The total point calculated is 13, and the maximum in which is not exceeding the maximum point, so the point awarded is 13. This is the summary of IBS score. For other IBS components, we're not consider repetition of structural layout in this project. So only utilization of standardized components and productivity enhancing solution and technology adoption. The total point awarded for other IBS components is 27, which not exceeding the maximum point of 30, so the point awarded is also 27. Thus, for all the parts 1 and 2 and 3, which are structure system, wall system, other simplified construction solution, the total point awarded is 93.01.
So we go to slide justification IBS adoption. So as you can see, why IBS is used in this project. So IBS is added to replace conventional construction with a standard system. So improve quality control and construction speed. So design follow by modular coordination, which is MC and JKR IBS developed. So this project uses IBS to shift from conventional on-site construction to a standard prefabrication approach. So we had improved construction quality and shorten the project duration. For this project, IBS was adopted to replace conventional construction and standard prefabrication approach, which improves quality control and speed up the construction process. So under the second point, the design should follow modular coordination, and the JKR IBS catalog. All non-modular architectural and structural dimensions were applied to the nearest standard size to ensure compatibility with precast manufacturing. So, precast construction pri- was prioritized for high volume components such as beam, column, slab, and wall that maximize efficiency and reduce material waste. So, however, components with complex geometry and low repetition, such as staircase, were constructed using in-situ reinforced concrete. So, a precast solution would not be economical. This balanced approach ensure that IGS is applied efficiently while maintaining technical and economical feasibility. So we go to overall outcome. You see, the precast used for high volume component, reduce waste and construction time, and maintain technical and economical feasibility, which is by focusing IDS on high volume components such as beam, slab, and wall. This project achieves high efficiency without incurring unnecessary customization costs. So that's all for me. Thank you.
In conclusion, the Phase 5 housing development successfully integrated IBS with a final IBS score of 93.01, exceeding the minimum requirement of 70 points for government projects. This achievement shows a strong commitment to industrial construction methods. The structural system was the main contributor in this project, scoring a 48.94 points through a use of precast beams, columns, and half steps, while the wall system contributed 17.07 points, while the remaining 27 points came from simplified solutions. These include 100% of modular grid line application and the use of BIM Level 2 and augmented reality during the planning stage. Overall, the project successfully implemented IBS in aligning component size with the JKR IBS catalog and can improve the productivity and quality while remaining technically and economically feasible. That's all for our project. Thank you.